All right, everybody, it's Miss Kennedy, and I'm about to change your life with a way to think about the unit circle, so prepare yourselves. The stuff on the left, we'll take a look at the way that you've probably thought of the unit circle in the past. It's on the right. You can see I talk about steepness there. That can make a lot of things easier for you. Let's start with what you have almost certainly seen before, of just the definitions of sine and cosine and tangent and all those things. You may very well have learned these in terms of coordinates and relationships between those coordinates, and of course that is completely fine. I'm also going to show you how you can think of it geometrically and how that can help us do some tough things easily. So hopefully you remember that cosine is the x-coordinate of a point on the unit circle that's at the given angle. Sine is the y-coordinate of that point. And then tangent, you might have remembered, there are different ways folks teach this, you might have remembered it as y over x, you might have remembered it as sine of the angle over cosine of the angle, which makes sense because y is sine of the angle and x is cosine of the angle. And all of that is true, and all of that is fine. But something that helps us work backwards, which otherwise can be quite difficult, is to think of this not just as a point, but as a triangle. So I drew a triangle, obviously. Got a right triangle. And I would certainly imagine you saw this type of idea when you first started discussing the unit circle. So that point on the unit circle with an x-coordinate and a y-coordinate is exactly 1 unit away from the origin. That's why it's called the unit circle. Instead of just thinking of cosine as the x-coordinate, I'm going to think of cosine as the width of that triangle that I drew. Likewise, I'm going to think of the y-coordinate as the height of that triangle, which makes sense because that's how I plot a point. I go over and up by the x-coordinate and the y-coordinate. But then this is the trick that honestly I didn't think about until I was in college, like a couple years in as a math major, and it made so many things so much easier. If you think about this y over x definition, or sine of theta over cosine of theta, that can get annoying. I have to do like 1/2 divided by the square root of 3 over 2, and then you have to do weird stuff with canceling or reciprocals. But if you think about it geometrically, the y-coordinate, that sine value, we could think of that as the rise of something. And cosine, or the x value, we can think of that as the run. And so really tangent is a rise over run on that triangle. And so tangent ends up being the slope of the radius. So this radius with a length of 1, its slope or its steepness is actually exactly what tangent is. And hold on to that idea because that's something that will help us on the right-hand side. But again, big idea here that doesn't always get taught in pre-calc. Again, it's not something I myself even thought of until college, is that the tangent of this angle down here can be thought of as the slope of that green radius. The next part will go a little bit quicker. Secant. You may have remembered that as 1 over the x-coordinate. That's fine. You might have remembered that as 1 over cosine of the angle. But really, instead of 1 over something, that just means reciprocal. And so instead of trying to do 1 divided by something, just flip it upside down. Same thing for cosecant. Cosecant of an angle, you might have remembered that as 1 over the y-coordinate, which is 1 over sine of the angle, but really, it's just the upside down version, the reciprocal, of sine theta. So if you know sine of an angle, you automatically know cosecant by flipping it. And then cotangent, you might have remembered that as, see, I didn't remember it. I got it backwards. As x over y, you might remember that as cosine theta over sine theta. Again, those are true, but it's really just the reciprocal of tangent theta. So if you know sine, cosine, and tangent, then you also know cosecant, secant, and cotangent just by flipping them upside down. You don't have to do weird division tricks. And again, that's going to help us with the big trick that we'll look at on the right-hand side. In order to prepare for that big trick on the right-hand side, I just want to make a list of sine and cosine values that you have for your memorized angles. So like your pi over 6, your 4 pi over 3, 3 pi over 2, all of those types of things. And I'm going to list them basically in smallest to biggest order. Ignoring the positives and negatives, all of these could be positive or negative. But the biggest that sine and cosine could possibly turn out to be would be positive 1, and the smallest would be negative 1. The other extreme would be 0. So again, I'm kind of ignoring the plus or minus issue right now. I'm just thinking in terms of absolute value, not the sign, S-I-G-N. So 1 is sort of the biggest I can get. 0 is the closest to 0 I could get, I suppose. And then your other memorized options, you've got a square root of 2 over 2. You have a 1 over 2. And you have a square root of 3 over 2. All of your memorized sine and cosine values are either positive or negative. 1/2 square root of 2 over 2, square root of 3 over 2, 1, or 0. And just while we're at it, kind of another fun little pattern is really that square root of 1 over 2. And then this last guy, you could think of that as the square root of 4 over 2. There are just lots of cool patterns happening in here that maybe you haven't noticed, or maybe you're more observant than I was in high school. So because secant is just the reciprocal of cosine, and cosecant is just the reciprocal of sine, all we're going to do is flip these guys upside down. Now flipping a 0 upside down gets a little weird, but we'll deal with that. So again, these might be positive or negative. We'll deal with the 0 in just a minute, but if I flip 1/2 upside down, well then I hope you know that that is 2. If I take the reciprocal of square root of 2 over 2, you could write that as 2 over square root of 2, and you would be right. Or, if you rationalize that, if I multiply top and bottom by square root of 2, that simplifies to square root of 2. If you don't believe me, try it on your own. This square root of 3 over 2, I can flip that upside down. 2 over square root of 3. If I rationalized it, then I get 2 square root of 3 over 3, but that's kind of a mess, so I'm not even going to bother with that. If I flip a 1 upside down, well, its reciprocal is still 1. So each of these has a reciprocal except for 0. If I do the reciprocal of a teeny tiny number, then I'm going to get an enormous number. If I do 1 divided by 0.00000000001, then I'm going to get an enormous number. And the closer this gets to 0, the crazier its reciprocal gets. And so we can say undefined. Some people will also get into positive infinity, negative infinity, but undefined will do what we need it to do. That list that we just created is going to be helpful for the big trick that I keep alluding to, and I promise it's coming. But before the big trick, let's take a look at our tangent values. We have some memorized tangent values. Again, these might be positive or negative, depending on which quadrant you're in. And here, again, I'm going to sort of list them from smallest to biggest, but that gets a little bit strange here. But for all of your memorized angles, again, your pi over 6 and so on, the smallest that tangent could possibly be is 0 until it becomes negative. And of course, that's how 0 works. The quote-unquote biggest it could be, this is where it gets a little bit funky, you have a couple of angles where tangent is undefined. And I'm going to think of that essentially as an infinity or a negative infinity. So that's the opposite extreme from a 0. In our ordered list, smack dab in the middle is going to be 1. You also have some memorized angles that have a tangent that turns out to be square root of 3. You also have some memorized angles where the tangent turns out to be either 1 over square root of 3, you might have memorized it that way, or square root of 3 over 3. You might have rationalized it and remembered it that way. But this is our list of 1, 2, 3, 4, 5 possible results for tangent. Well, if I flip those upside down, I'm going to get all of my cotangent values. Again, maybe positive, maybe negative. The 0, when I flip that upside down, I get kind of infinity, maybe negative infinity. We'll just say undefined. This 1 over square root of 3, we'll flip that upside down and it's a square root of 3. The reciprocal of 1 is still 1. The reciprocal of square root of 3 could be written as 1 over square root of 3. Look familiar? Or you could rationalize to square root of 3 over 3. And you'll notice that matches what we had over there. Likewise, the weirdest thing on this list, but it already has a partner, is that if I take something that's undefined, because it's essentially infinite, well then its reciprocal, quote unquote, is a 0. Again, that's just a match of this pattern on the left, just reversed there on the right. So those lists, and then that triangle idea at the top, those are the secret to what I have over here on the right. Because I've drawn the unit circle with all of our pi over 6s, pi over 4, pi over 3, pi over 2, and then just full multiples of pi. And so my horizontal radii, again, thinking of this really geometrically, I teach geometry too, so that happens a lot. This spot over here, you might think of that as 0 pi, or 2 pi, or 4 pi, or negative 68 pi. This one on the left, maybe a pi, or 3 pi, or so on. So I'm going to think of those horizontals as just being whole multiples of pi. And that's a little bit odd, so I'm going to actually move on to something a little bit more interesting. So you'll see that I have these organized by steepness. So for me, when I think of not so steep, this is the radius I'm imagining in quadrant 1. If I'm in quadrant 2, this is my not so steep guy. Quadrant 3, quadrant 4. Hit spacebar and pause for just a moment and see if you can remember what the denominator is for each of those blue guys. Are you back? Hopefully you remembered that this spot was pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So all 4 of those not so steep guys have denominators of 6. The in the middle guys, let me get a purple here. So the ones that are not super steep, not super shallow, this is a pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those guys that are just kind of in the middle. They're not super steep like this pink one. They're not shallow like the blue, they're just kind of smack dab in the middle. They're like a 45-degree angle, or pi over 4 radians. And then let's take a look at the steeper ones in each quadrant. So this steep guy is pi over 3, 2 pi over 3, 3 pi over 3 is over here, 4 pi over 3, 5 pi over 3, and then 6 pi over 3 would get me back to where I started. So those steep pink ones are all something over 3, even after I reduce them. And then the strangest of all, the vertical. I have a pi over 2 and a 3 pi over 2. Okay, so that took us a while to get there, but I promise I'm going somewhere with it. As a reminder, the cosine of the angle, I'm going to think of that not just as an x-coordinate, but as the width of a triangle. So this green guy, well, that barely even counts as a triangle, but it's awfully wide, isn't it? So that's my maximum cosine, maybe positive if I'm on the right, or negative if I'm on the left. And as we saw earlier, if I know that cosine is plus or minus 1, well then take a reciprocal. It's my very fancy reciprocal symbol. If cosine is 1, then that reciprocal is still 1. If cosine was negative 1, then secant of the angle is also negative 1. Okay. For the blue guy, I'm going to actually draw that triangle similar to what I did on the left, so you can really see what I'm talking about here. So what happens in my brain, and I've just been doing it for 20 some odd years, oh god, longer than that. That's okay, it's fine, I'm having a nervous breakdown. But what happens in my brain when I'm trying to think of sine and cosine and all these things is I think, okay, for pi over 6, it's not very steep, and so cosine, the width, has to be pretty big. The height is not very tall, but it's a pretty wide triangle. So I think through my list of options for sine and cosine, and I say, the big one, but not the biggest, is square root of 3 over 2. Might be positive, might be negative, and that tells me secant is 2 over the square root of 3. And you can rationalize if you want to. Honestly, in AP Calculus, we don't even bother rationalizing for final answers. Let's continue with that blue one, just so you can get a feel for what this trick is for something that actually looks like a triangle. The green one, not so much a triangle. So I know that sine of the angle is the y-coordinate of the point, but like I said, I'm going to think of that as the height of the triangle. That blue triangle is not very tall. And so if I think through my list of options for sine and cosine, well then the not very big one is 1/2. Maybe positive, maybe negative, and I would just imagine, based on the quadrant, whether that should be positive or negative, whether my height is going upward to be positive or downward to be negative. And then I automatically know cosecant is the reciprocal, so 1/2 turns into a 2. And you might have come up with those tricks last year in Precalculus. You might have come up with them on your own or been taught those explicitly. But as I've said a couple times, it's this tangent one that to me is the really helpful trick. Because for tangent, I'm not going to think of that as y over x. I'm not going to think of it as sine theta over cosine theta. I am going to think one word, slope. Maybe 3 words, slope of radius. So when I look at this blue triangle, that radius right there is not so steep. And so I think through my tangent options. Out of these tangent options here in blue, the one that's not so big is this 1 over square root of 3. or square root of 3 over 3, whichever you prefer. Might be positive, might be negative. And the way that I can decide positive or negative, again, is based on the quadrant. I don't have to do, if you learned the all students take calculus or whatever it is, you don't need it. You don't need a goofy mnemonic to help you remember how slope works. Because when I'm in quadrant 1, the slope of that radius is positive, so tangent of that angle is positive. In quadrant 2, the slope of that radius is negative, so tangent is negative. Positive slope, positive tangent. Negative slope, negative tangent. I don't need a mnemonic device for that. I just need the visual of a slope going uphill or downhill. And so then, if I know tangent, I automatically know cotangent just by flipping that upside down. So then let's take a look together at the green one, and then the purple and pink and red. I'll let you guys try those on your own. But these green ones are a little bit weird. We already said, okay, well, that's not even really a triangle. I can't make a triangle. So for that green horizontal, I'm going to give it the maximum width, either positive 1 or negative 1, depending on which direction I'm headed. But that's not even a triangle. It doesn't have any height. So I know that sine, for those green guys, has to be 0. And if sine is 0, I know that in some sense the reciprocal of 0 is undefined. It's not quite true, but it's kind of a memory trick. And then the slope idea helps me out down here. If I look at that horizontal radius, the horizontal segment, the slope of any horizontal line is 0. So tangent of 0 pi is 0. Tangent of 1 pi is 0. And so on, because those radii are horizontal. I don't have to do division and try to remember which one goes on top or bottom. It's just a slope question. And if tangent is 0, then cotangent is undefined. So you can pause the video at this point. In fact, I encourage you to do so. And try to fill in those other 3 columns using some of these width, height, and slope tricks, rather than relying on x's and y's and drawing out a unit circle and dividing things and bleh. See if this helps. So pause the video, and when you're ready, unpause, and I will have answers for you. All right, take a moment and see how you did. You'll notice that for some of these, there are different ways to write the same answer. But another weird one is those verticals. But weird is actually great news because they're easier. A vertical segment, well, that triangle has no width, so cosine is 0. That vertical segment has only height, so I max out sine at either positive 1 or negative 1. And then if I think of slope, vertical lines have undefined slope. So without trying to do any like division thing and like, can I divide by 0? Can I divide things that are 0? Whatever. Undefined slope, vertical line, and you're done. So a lot just happened. The left side is probably mostly familiar. It's that right-hand side, and especially this right here, that I think might make a difference for helping you remember some of this stuff. So I hope that helps.